We saw what randomized algorithms are. In the video today, we are going to see another relaxation from the deterministic algorithm. In the deterministic algorithm, we want to compute everything exactly and all the time. The relaxation this time is going to be that we are fine with even approximate answers. Before we talk about approximation algorithms, I want to talk about Bernstein-Verzani algorithm, which is a modification of W6L2. And let me emphasize why we need this modification. If you remember W6L2 algorithm, the amount of quantum queries needed for it were just one. On the other hand, if we wanted to exactly compute the answer, then we need to do at least n by 2 queries, which we call theta. But now you know another model, randomized queries model. So if on a classical computer, you want to make a randomized algorithm and ask how fast you can solve it, we know that only a few queries suffice, only a constant number of queries suffice. This separation is not very impressive. I can do it in one query on a quantum computer, I can do it in a few queries on a randomized computer. What I want to show you is that even this gap can be enlarged, and that will be shown by Bernstein-Verzani algorithm. It will show a separation between quantum and randomized model. Notice that when I talk about randomized, I mean classical randomized. Quantum algorithms are going to be randomized. We're going to check their performance in the randomized conditions. But when we talk about this, we mean a classical algorithm with randomized model guarantees. Okay, let's define our problem. Again, it is going to be a promise, means that our input is going to be from this, it is going to be a binary string of length to the power k, but only certain substrings are allowed. What is the condition? The ith bit will be I dot a for some hidden string a, which is an element of 0, 1 to the k. Remember, I can be thought of as an index from 1 to n. A better way to note it would be n, or I can also be thought of as a binary string of length k. Now, when I talk about I here, this is an index. When I talk about I here, I'm taking an inner product. At this point, I'm thinking of it as a binary string. And then I dot a is a usual inner product in the F2 domain. That means I just take entry-wise product, sum them up, and find out whether it is even or odd. This is what this condition is saying. Once again, Bernstein-Verzani problem says that we have inputs of a very special kind, so that every xi is of the form I dot a. The task is to find a. We will again have oracle access to x. We can always ask what is the ith bit of x. It will take us one query. We will be charged one query for it, and using minimum number of queries, we want to figure out a. Given that this condition is true. If you think about it a bit, this is very much like Deutsch-Jotzer. When A is equal to 0, I dot A will always be 0. When I say equal to 0, I mean it is all zeros. In that case, I dot A is equal to 0. This corresponds to x being constant. On the other hand, if A is not equal to 0, then you can show that I dot A will be 0 half the times and 1 half the time. This is the balanced case. In that sense, Bernstein-Masrani problem is a special case of Bayes' problem, but in this case, we want to output. How can we solve this problem? It's a special case of Deutsch-Jotzer, but we need kind of a bigger output. It just doesn't, it isn't enough to say whether our input is balanced or constant. We have to say what A we are hiding. It turns out that the same algorithm works. That might seem surprising, but let's see how. Let me remind you what was Deutsch's algorithm. We started with state 0, 1. There is no summation here. We created an equal superposition. This was using Hadamard. Then we queried. This gave a phase. And then we again applied Hadamard. This collected the amplitude on 0. It turns out that the amplitude on state 0 after that was going to be minus 1 to the xi. This was 0 if xi was x, I should not say xi, but I should say x was balanced, and 1, there will be a normalization factor, 1 if x is constant. This was the simple algorithm. I'm going to follow the same thing, but let me ask this question. What will be the amplitude on other states? I have calculated the amplitude on state 0 for the Deutsch-Jotzer algorithm, but what will be the amplitude on other states like 0001, 1111? Can we figure out the amplitude here on the other basis states? In other words, we want to figure out how this Hadamard operates on the state. Let us see. The first thing to notice is that if my state is J and if I apply Hadamard on it, then I will get, this is the normalization factor, I'm sure you can figure it out, but the amplitude on state I is going to be this. This is something which you can verify easily. Remember that I will get a phase of -1 if both the coordinates are 1. If I look at IL and JL going from GL to IL will give me a phase of -1 only if both the coordinates are 1. And then this counts the total number of -1s incurred. Knowing this, it is easy to figure out the amplitude of other states. Remember, my state was this. If I want to be precise, I will write a normalization condition and then the amplitude on state L this is going to be, this is what every I will contribute. First xi, this is coming from here, and then another factor of I dot L. This is because of the header mode. This is what the state I will contribute, and then we will sum up over I. Let me write it on a new page, and then we will see that this is actually in a very good form. Again, this comes from the state, and this comes from applying header. This is the total amplitude on state L. Let me simplify this. Notice that xi is -1 to the power I dot A. This amplitude is 1 over 2 to the k -1 to the, and this is very simple. This summation is almost always 0. It will only be non-zero when this A XOR L is the all zero string. This is something we saw before also. If A XOR L is all 0, then you will always get a phase of 1, and then this thing will become 1. Otherwise, half of them will be -1, half of them will be 1, and this will cancel out. This is the property of header mode. And A plus L being 0 is same as A is equal to L. That is great. After applying the header mode in W6L2 algorithm, the final state in W6L2 algorithm is going to be just A. We did not change anything in the algorithm, we just calculated the final amplitude. It turns out that the amplitude of L was 0 if L was not equal to A and 1 if L was equal to A. That basically means that our final state is going to be A. We measure in standard basis, and that will give us the hidden A. That will complete the algorithm. We finally get the hidden string L. This says that quantumly we just need one query, like the W6 algorithm. But if you look at randomized algorithm, it turns out that you need at least theta log n queries. The proof is outside the scope of this course. Just I will tell that the intuition behind the algorithm is that each bit of A needs at least one query. Remember, log n is like k, which is the length of the string, length of A. So each bit, to figure out each bit of A, we need at least one query, and hence you need theta log n. This is an information theoretic argument, and we don't know information theory, so I will skip the complete argument. We have seen separation between quantum and randomistic model. We have seen the difference between quantum and randomized model. Completing the algorithms part, for the sake of completeness, I just want to describe approximation algorithms. This is in a very different genre. The idea is that we define randomized algorithms as being a relaxation of normal algorithms, which compute everything exactly. We can define a relaxation in a slightly different way, which is going to be called an approximation algorithm. This happens for tasks when we want to optimize some function. What does it mean? You will be given some input, and then there are going to be a lot of parameters. We choose some, we will get f of s. And then our task is to min or max, find the maximum of this f of s. This would be clear with an example. For example, in the shortest path case, my G will be a graph. S would be a path between S and T. And F would be the length of the path. We want to find the minimum of f of s. This is our task in the shortest path problem. You can look at many problems like vertex cover problem, independent set problem. In many of these, the same scenario exists. There is an input, there is a parameter. If we choose that, we get some quantity. We want to minimize that quantity or maximize that quantity. Let's keep with the minimum. In that case, there is an optimal choice which actually minimizes this f of s, and then the answer of the algorithm should be f of s0. This is what we want to find out. This is the global minimum or maxima. In the case of approximation algorithm, we allow a relaxation. We say that we only want to output, so on G input, our algorithm will output something whose value should not be much bigger than the optimal. Remember, this is the min case. And C here is a constant greater than 1. For the max case, the algorithm should output something which is bigger than some constant times an optimum. This time the constant would be less than equal to 1. This is the guarantee. So instead of answering the exact value, we are fine even if it is slightly bigger or slightly smaller than the actual value. This is slightly different from randomized algorithm. Sometimes people get confused, and that could be explained by a picture. Let's say our task is to hit a bull's eye in the game of darts. In the case of randomized algorithm, we want most of our arrows to hit the bull's eye. Rest of them can go anywhere. In case of approximation algorithm, we want all our arrows to be close to the bullseye. This is the main difference between these two kinds of algorithms. This finishes the video. Thank you.